let's continue our morning session. It's a pleasure to welcome John Brundan from the University of Oregon. And John will tell us about Isomeric Heisenberg and categorification.
Okay, great, thank you. Is this microphone in the right place? Perfect. Okay, let me just give a couple more minutes for people to sit down. Okay, so I guess before I actually start the talk, I have this opening slide, which is kind of my view of representation theory. So you study representation theory of any sort of Lie type. For me, that's synonymous with studying combinatorics of projective functors. And I guess the dominant genre for understanding combinatorics and projective functors is really Zergel's point of view, combinatorics of Harish-Chandra bimodules or Zergel bimodules. This is not a talk that goes in that direction. It's wonderful in that direction, and it's kind of uniform in all Lie types are sort of treated in the same way. So there's no surprise it's the dominant genre. It's certainly wonderful. But if you look at the individual classical groups, instead of studying Janssen's translation functors or reflection functors, there's another source of special projective functors that appear just by tensing with the natural representation of your classical group. And this leads to a kind of independent alternative way of setting up the framework of projective functors, which is kind of special to the type of classical group that you're studying. And it's somehow you go down this path and it opens up a completely different vista, independent of the Zergel bimodule story. And I think Wei Chung, in his talk at the end, he had this fourfold way mentioned as well. There's really four families of classical supergroup. There's the linear family, and there's the orthosymplectic family, the periplectic family. This is you only see this if you go up to superalgebra, and this talk, I'm going to be talking about the type Q family, which I want everybody to be calling the isomeric family. That's a new name which was suggested by Andrew Snowden that I think is a good name for type Q, the isomeric supergroup. Anyway, so in all of these four families of classical supergroup, there will be a kind of a categorification story like the one that I'm telling you today, and I'm just telling you it in the isomeric case. This story is very well developed in the linear case. That's the story I call Heisenberg and Moody categorification, and it opens up this tremendous path towards these beautiful diagrammatic categories called Moody two categories. The Heisenberg category there is Michael's Heisenberg category in its generalizations, and so here the story is in a very satisfactory situation, and I'm not going to talk about that. I'm going to talk about the type Q case where we're getting close to the same level of satisfaction. And then the orthosymplectic case is in earlier days. It's not as well developed, but it has to do with this affine-Brauer category and categorification of I quantum groups. That's what that OSP avenue opens up, those perspectives. And I know nothing about the type P case, but I'm sure that's also a beautiful story. So let me now begin properly. K is going to be an algebraically closed field of characteristic P not equal to 2. This talk is going to be enriched in the symmetric monoidal category of vector superspaces. So SVEC there. This is a very tame symmetric monoidal category to enrich in, and I'm not going to say much about it, but But the point is, this takes care of lots of signs, which are very annoying if you don't take enrichment seriously. I was first taught how to take enrichment seriously actually by John Kuyaba here. So it's very important to systematically use the whole language of enriched category theory, enriching in spec for this to work. So let me just give a tiny little piece of language about enriching in supervector spaces. So I use some slightly strange terminology which might not be familiar. I use the term supercategory for a category that's enriched in spec. It means that the morphism sets actually are vector superspaces in a supercategory. The composition of morphisms preserves parity of those morphisms. I use the term superfunctor for an enriched functor. So that's a functor in the usual sense, which on these morphism superspaces induces a parity preserving linear map between those morphism superspaces. And then I use this great term, I think I learned this from a paper of Michael and Aaron. It's the first time I think I maybe saw it, this term supernatural transformation. So this is the appropriate enriched notion of natural transformation. If you set up the fully enriched version of your dilemma, this is what plays the role of natural transformation when you do that, supernatural transformation. So let me see, if you have supercategories A and B, and you have a pair of superfunctors E and F from A to B, a supernatural transformation alpha from E to F, well, it's data of morphisms alpha X from EX to FX, varying object X of the category A, and then you need these naturality squares. Well, in this case, they're supernaturality squares. So I've taken a morphism F from X to Y in the category A. This morphism F, it might not be even. It might not even be homogeneous in general, right? Because these morphism spaces are vector superspaces. And I've applied the functor E to F and the functor F to F. And this is the morphisms, it's the data of my supernatural transformation. And the requirement is not that this diagram commutes, but that this diagram supercommutes. That means that if all four morphisms are odd, then actually going one way, you get minus the composition the other. So these kind of, it's not the same as a natural transformation when everything is odd, but it's the right notion that you should work with. Then the other construction from enriched category theory, which is very tame in this when you're enriching in spec. If you have two supercategories A and B, there's a supercategory from A, B. This is the enriched functor category. It just consists of superfunctors from A to B, and then the morphisms are supernatural transformations between those superfunctors. So it all seems silly, right? You just put the word super in front of everything you normally say. But this is burying a lot of very difficult signs that otherwise would be hard to manage. So in particular, if you take a supercategory A, the enriched functor category end A, that's a supercategory, but it's even better. It's a monoidal supercategory because you can if you have supernatural transformations, you can compose them vertically and you can also compose them horizontally. So that makes this into a monoidal supercategory. And when I'm working with, well, in fact, this is even better. It's a strict monoidal supercategory. When I'm working with strict monoidal supercategories, I'll use the usual string calculus. I think that's familiar. So, but just my conventions are the same as in Wei Cheng's talk. F composed with G is my vertical composition. I put F on top of G in the string diagram, and F tensor G, that's the horizontal composition. I put F to the left of G in the string diagram. And because these are string diagrams for monoidal supercategories, we were enriched in spec. When you think about the interchange law in this world, if you change the vertical height of two of these coupons, F and G, you get a sign. If F and G are both odd, if P of F, the parity of F, and the parity of G are both 1, you get a minus sign in it. So this is part of not equal. Do you mean equal minus 1 or times minus 1? Oh, it doesn't show up on that. I don't understand this. You're missing half the slide here. So what do I have to do to get the whole slide to appear? No, but this is, you can't see the end of the picture. The right-hand edge is missed. Yeah. How do I fix that? I didn't notice that.
Can you zoom in a little bit? So let's do
it's fine on that.
Okay, so let's do a quick fix. Okay, let's use this name.
All right.
Okay, so
great. I'll have to use the mouse. It's fine.
No. All right.
Okay, great.
You can do whatever you do here.
And this
It's
still
okay.
works here?
Yes.
Okay.
Right.
It's not quite as good, but hopefully people can actually see everything you're meant to see. So now you see what I'm talking about with changing the vertical level. It was clear to me what's going on. Okay. So that's because we're enriched in supervector spaces. These signs, when you change vertical height, it's built in automatically. Okay. The last piece of kind of general nonsense about supercategories, which I'll need later on, is the notion of a Clifford twist. So if you have a supercategory A, I will use the Clifford twist of A Clifford twist. It's a straightforward construction. It's a new supercategory whose objects are pairs, x comma phi, an object x of the original A, and then phi is meant to be an odd endomorphism of x whose square is -1. So in the Clifford twist, objects are pairs, and in the Clifford twist morphism between two such pairs is just a morphism between the underlying objects in A, such that the obvious diagram commutes. So that these odd maps, theta and phi, part of the Clifford twist data are compatible with each other. If your category A is idempotent complete Caribbean, then the Clifford twist is as well. And if you Clifford twist twice, you get a category which isn't actually A, but it's super equivalent to A. So this is a reasonable construction. Very easy example is if you take actually just a superalgebra. So this is A in a different font, just a regular superalgebra. And you take your supercategory to be the supercategory of left A supermodules, then the Clifford twist of that category is exactly the same as the category of supermodules for the superalgebra that's A tensored a rank 1 Clifford algebra C. So I use C for the superalgebra with an odd generator, little c, whose square is -1. That's the rank 1 Clifford algebra, big C. And Clifford twisting supermodules over a superalgebra is just another way of getting supermodules for that new superalgebra, A tensored, the rank 1 Clifford algebra. And in this way, you can see why A supermodule Clifford twisted twice. Well, that's just supermodules over A tensored the Clifford superalgebra C tensor C, which is the rank 2 Clifford superalgebra. And the rank 2 Clifford superalgebra, that's just a full matrix algebra of 2 by 2 matrices. So this guy is Morita equivalent to the original A. That's this in that explicit example why the double Clifford twist is equivalent to the first. Yeah, so that's all the general nonsense. Everything's enriched in supervector spaces. It's a very nice natural setup. Okay, so the main object of interest for this talk, it's something that I call the Isomeric Heisenberg category. So this is now the first important definition that everyone should wake up for. So this is the isomeric analog of Khovanov's Heisenberg category. So it's denoted Heis sub kappa of C. The C in there is that rank 1 Clifford algebra that I had before. And kappa is any integer. I usually call kappa the central charge. You can fix a central charge kappa. So by definition, the isomeric Heisenberg category, it's the strict monoidal supercategory has two generating objects called E and F. I denote, when I'm drawing these string diagrams, I denote their identity morphisms, the identity of E by an upstring and the identity of F by a downstring. And then there are some generating morphisms. There's the dot. So I draw the dot. It's the same dot that was in Wei Chung's talk, but I draw that with an open circle. That's the dot. And I use the closed dots there. I call that a Clifford token. So there's the Clifford token, there's the dot, that open circle, and the crossing. And then the other two generators are this rightward cap and this rightward cup. I think most of you are really familiar with this string calculus, so I don't need to say much more about it. This is a monoidal supercategory. So I've got to make my generating morphisms, I've got to tell you their parities, what the Z2 grading is for them. And the Clifford token is odd. That solid black dot is odd. All the other generating morphisms are even. And then there's relations satisfied by these generating morphisms. In fact, there's 4 families of relations. I'm going to write them fairly quickly. So here's the first family of relations. There's the Clifford token. The Clifford token squares to -1. It's that first relation. Just like C squared was -1 in my rank 1 Clifford algebra C. The way the dot and the Clifford token commute, there's a minus sign there when dot and Clifford token commute. And then the other relations should look pretty familiar, just like in the symmetric category that you saw in Wei Chung's talk. The Clifford token just slides across the crossing. So the dot slides across the crossing in a slightly more subtle way. If this last term wasn't here, that was exactly that degenerate affine Hecke algebra relation that was in Wei Chung's talk. But in the isomeric case, there's this extra term where there's these 2 Clifford tokens appearing. But if you were to take that definition and erase everything that involved the Clifford token, throw away the Clifford token as a generator, throw away all the relations that involve the Clifford token, that's the usual presentation for Khovanov's Heisenberg category. So it's Khovanov's together with this extra Clifford token. So that's the first family of relations. Maybe you're familiar with this subject. These are the relations of what's called the affine Sergeev superalgebra. The second family of relations are the zigzag relations. That's just saying that F is a right dual to E. But it's kind of handy to have these shorthands. Once you have this rightward cup and rightward cap, you can kind of rotate the generating morphisms. So you can define the Clifford token on a downward strand. You can define the dot on a downward strand. You can rotate the crossing to 90 degrees to get the rightward crossing. Then you can rotate that again to get the downward crossing. So those are just shorthands for other morphisms built using the generating morphisms. The third relation is maybe the difficult one to cope with. It depends on kappa. Let me just explain this when the central charge kappa is less than or equal to 0. I've written down this great big row vector. This is a row vector of morphism. Sideways crossing that cup with a dot with a Clifford token, and then sort of Clifford token, no Clifford token. Then there's a dot and a Clifford token and a dot, and so on, all the way here, where there's minus kappa -1 dots and a Clifford token. And finally, minus kappa -1 dot. So this is a great big row vector. It's really a morphism from a direct sum, E tensor F, direct sum, lots of copies of the identity morphism. Each of these cups go from the identity to Fe. So this matrix, it's a matrix of morphisms from that direct sum to F tensor E. And relation 3 simply says that matrix has to be inverted. It's a sneaky way of saying there are other generating morphisms that give you entries of a matrix, which is the 2-sided inverse of this matrix. And then the final relation is easy to state. I also impose that all endomorphisms of the identity object, or odd endomorphisms of the identity object, are required to be 0. This simplifies things quite a lot. But it's really just a technical simplification that you could really avoid. Okay, so it's a bit meaningless seeing a definition of a monoidal category by generating some relations here. In fact, this Heis kappa of C, the Isomeric Heisenberg category, it's a special case of a much more general construction of Alistair Savage, where he defines something he calls the Frobenius Heisenberg category, starting from any Frobenius algebra. And I'm just taking the Frobenius algebra in that general construction to be this rank 1 Clifford algebra. Yeah, so it's an entirely elementary definition. Just go back again. This Isomeric Heisenberg category, it's just a strict monoidal supercategory with this very simple and clean set of generates and relations. The place the central charge kappa appears is in this inversion relation, that the nature of that matrix that I wrote down depends on the choice of the central charge. If kappa is 0, that matrix is particularly easy. It's just the rightward crossing. It's a 1-by-1 matrix. And it's just saying that the rightward crossing has to have a two-sided inverse. Okay, so that's the main object of study, this Isomeric Heisenberg category. The main problem, I want to understand the structure. Okay, so I've got A here. So A is always from now on going to be a supercategory. It's actually going to be a finite, I want to be a bit more careful there. I don't mean finite, I mean locally finite abelian supercategory. So by that I mean I want A to be a supercategory, which if you look at the underlying category, so you just consider only the even morphisms. I want that to be an abelian category in the usual sense. In fact, I want that to be a locally finite abelian category in the usual sense. So I just call A locally finite abelian supercategory. And I want to have an action of this Isomeric Heisenberg category on that abelian category A. So A should be a module supercategory over my Heisenberg. Put another way, there's given data of a strict monoidal superfunctor from this Isomeric Heisenberg category to the strict monoidal category end of that supercategory. Does that make sense? Okay, so I'm really interested in understanding these locally finite abelian supercategories A, where I can find some action of this Heisenberg category on. That's going to give an amazing amount of tools to kind of crack that category A with. That's what we're interested in. So I want to kind of give you two examples to convince you that this isn't really a silly setup. The first example of the category A comes from representations of double covers of symmetric groups. So so Sn hat is just one of the double covers of the symmetry group Sn. So there's this exact sequence of groups here. I actually care about the group algebra of the double cover, where the central element Z is specialized to -1. So that's often called the twisted group algebra of the symmetric group. So I'm interested in studying representations of that twisted group algebra, which is the same as studying projective representations of the symmetric group Sn. And if I take that algebra and I view it as a superalgebra, so that permutation, a basis element given by a permutation, is a parity just given by the sign of that permutation, even or odd, according to that permutation. So transpositions are odd. And then I tensor that superalgebra with the rank n Clifford superalgebra. And this, of course, is tensor product. Everything's enriched in spec, so tensor product in the right sense with the right signs. That superalgebra is called Wn. And that's usually called the Sergeev superalgebra. And representations of Wn is roughly represent these projective representations of the symmetric group Sn, because the Clifford superalgebra is a simple superalgebra. But it's just much easier to study representations of Wn in this way rather than directly looking at projective representations of symmetric groups. There's this superalgebra Wn, and the category A that I like to study is just the direct sum over all n of the categories Wn supermodules, finite dimensional supermodules over all these Sergeev superalgebras W. This is an example of one of these locally finite abelian supercategories A, which comes equipped with an action of this isomeric Heisenberg category. In fact, the central charge in this case is -1. And this is very easy to construct. It's really, when you have an example, it's easy to see you have an example. The isomeric Heisenberg category was basically built from this Sergeev superalgebra. So the dot and the crossing and the token on the upstrand, they're kind of almost given because they were these affine Sergeev superalgebra relations. And so they're kind of obvious. You take the action of E, the generating object E of isomeric Heisenberg, just to be the usual induction functor, reducing from Wn to Wn plus 1. And you take F to be the restriction functor. So, and then this adjunction, the right cap and the right cup, they're the standard adjunction between induction and restriction. And the only thing that's difficult to check is this inversion relation, which in this case for central charge -1 is showing that this 1/3 matrix has to be invertible. So this is sideways crossing the cup with the Clifford token and the cup. So this is a natural transformation from induction after restriction, direct sum 2 copies of the identity functor, to restriction after induction. And this inversion relation is saying that this particular supernatural transformation has to be inverted. And if you think about it for a little bit, you realize this is exactly the Mackey theorem for representations of Wn relating induction and restriction between two neighboring algebras. But you have to actually write out the proof of the Mackey theorem to check the inversion relation. And then you've got that this isomeric Heisenberg acts on this category A, which is representations of all these Wn's, which up to this tensing with Clifford is these projective representations of symmetric groups over the field K. Remember, that was a characteristic anything not 2. But in positive characteristic, that's really a fascinating. So that's one example. Example 1, so roughly projective representations of symmetric groups in positive characteristics. And example 2, I decided example 1 was maybe quite a lot to swallow. Example 2, I tried to think of the simplest possible example that I could. So this is like the most basic baby example that there is, but I think it's even this is instructive. So let me quickly give you example 2. So example 2 comes from the Lie superalgebra Q1, which is an extremely silly Lie superalgebra. This is this isomeric Lie superalgebra Q1 over our field K. And I'm going to take the field K to be of characteristic 3. I'm trying to give you the most ridiculous baby example that there is. Actually, I'm not going to look at, so U of Q1, that's the unit, I should say what Q1 is, sorry. Q1 of K, it's a Lie superalgebra consisting of 1, 1 by 1, 1 matrices. So 1, 1 means even dimension 1, odd dimension 1. So matrices of this form, but with a Z2 grading, so the ones supported in the A's are even and the ones supported in the B entries are odd, under supercommutator. That's the Lie superalgebra Q1 of K. It's just 2-dimensional. It's got a basis given by the even matrix E, that's the identity matrix, and the odd matrix F. And then if you look at its universal enveloping superalgebra, that will have a PBW basis. There's just some power of E together with some power of E times F. I'm trying to make this the babyest, most easy example that you could possibly come up with. So I'm going to then quotient out the universal enveloping superalgebra of Q1 by the two-sided ideal generated by E cubed minus E. In other words, this is the reduced enveloping superalgebra in this case. So when you do that, I'm going to call that little u. You get an extremely easy superalgebra to understand. I'm in characteristic 3 as well. So that's why I did E cubed minus E. The power 3 is indeed perfect, right? But I'm trying to do the one that's the smallest example I can think of, and I'm not allowed to do characteristic 2, so it's characteristic 3. But of course, E cubed minus E, when you impose that relation, E is central in here. You get a quotient where there's just Chinese remainder theorem kicks in, and you get just the identity is a sum of 3 orthogonal idempotents coming from the roots 0, 1, and -1 of that polynomial. And so this little algebra U, it really is extremely easy. It's just a 6-dimensional algebra. It looks like K of F over F squared. F is odd, so that's just a kind of 2-dimensional Grassmann algebra. And then you get a K of F over F squared plus 1. That's a rank 1 Clifford algebra. And you get another K of F over F squared minus 1, another rank 1 Clifford algebra. That's the algebra little u. It's a totally silly example. It has 3 irreducible supermodules according to how E acts. If E acts as 0, then you just get a 1-dimensional. In fact, this is just the trivial module K of the Lie superalgebra Q1 in that case. And big pi there, that's the parity switching function. You're looking at supermodules. So you have this 1-dimensional trivial supermodule concentrated in parity 0, and then its parity flip pi k is concentrated in parity 1. They're not isomorphic by an even isomorphism, but they're isomorphic by an odd. So that's the irreducible coming from this block, and then from this block, the irreducible, the Clifford module for that Clifford superalgebra is that's just actually the natural module for Q1, the natural module of column vectors. So in this case, V is isomorphic to its parity flip. It is an isomeric irreducible module, just tautologically in this case. The matrix that I've written down there, 0, 1, -1, 0, that gives an odd isomorphism. That gives an odd automorphism of V. So that's why V is isomorphic to its parity flip by an even isomorphism. And then, of course, there's V star, the dual of the natural module, which is the Clifford module for that third sum. Here's an embarrassingly easy example, but it's still very instructive for what I'm going to do in a bit. So in this example, again, on the category of U supermodules, finite dimensional U supermodules, there's an action of this isomeric Heisenberg category. In this case, the central charge kappa is 0. The function E just acts as tensing with the natural representation. F acts as tensing with the dual natural representation. The crossing and the right cap and the right cup, they're kind of obvious. The Clifford token, so that's meant to be a natural transformation from E to E. It's just given by acting with, remember this matrix was this odd isomorphism from V to V. Act with that on the first position, you're acting on a kind of a V tensor M here, and do the identity on M. That's the Clifford token. And then the dot, it's a little bit strange, the dot. So this is meant to be an endomorphism of E again, so I need an even endomorphism of V tensor M for some U module M, and it's just given by acting with this matrix tensor E, direct sum, this guy we saw before. This was this odd symmetry tensor F. And you have to check that this is indeed a U supermodule endomorphism of V tensor M, and then you have to check that these supernatural transformations satisfy the defining relations of my Heisenberg category, but it's a straightforward check. Example 2, actually, there's a whole family of examples. Basically, any category of representations of anything QE, anything related to the isomeric supergroup, or its Lie superalgebra, or its Yangian, or its W algebra, or anything arising in that world should admit an action of this isomeric Heisenberg category. of central charge zero. So there's a whole load of wonderful examples that are interesting coming to you. Okay, so there's just two examples. Projective representations of symmetric groups fit into this framework. Anything related to the isomeric supergroup or Lie superalgebra fit into this framework. Okay, so let's go now back to the general case. So I'm back to the general case that I've got my locally finite abelian supercategory A equipped with a categorical action of this Isomeric Heisenberg category. I think I'm going to just tell you what happens when kappa is less than or equal to 0, just to keep things easy. So I've got to start telling you a few things about this Isomeric Heisenberg category. So the first, when you define a monoidal category diagrammatically in this way, the first question you should ask yourself, what are the endomorphisms of the identity object? So these are given by string diagrams where there's no strings at the bottom and there's no strings at the top, but you can kind of create and destroy some stuff in the middle using cups and caps. So these sort of endomorphisms are typically given by bubbles when you draw their string diagrams. So here's an example of a bubble, right? This is a counterclockwise bubble, and then there's n dots on the right-hand edge of that diagram. Such a bubble is an endomorphism of the identity object in this strict monoidal supercategory. In fact, the algebra end of 1 is freely generated by those dotted bubbles. This Isomeric Heisenberg category acts on my abelian category A. So these bubbles, which are endomorphisms of the identity object, will define endomorphisms of the identity functor from A to A under this action. Endomorphisms of the identity functor of A is just the center of that supercategory A. So these bubbles are really important because the way they act on the category A is by central elements. So great, we have all these dotted bubbles, which in this action give you loads of central elements on this abelian category. It's very convenient to put all these dotted bubbles. There you go. There's my dotted bubble with n dots. So I use the variable u just as a formal variable for generating functions. And I like to put all these dotted bubbles together into a great big generating function. So this is dotted bubble with n dots, u to the power minus n minus 1. I call that bubble of u. So that's just, it's a single gadget that's the generating function for all of these dotted bubbles. If I have an irreducible object L of the category A, this bubble of u will act by a formal series. I mean, by Schur's lemma, a central element acts on L by a scalar. So this bubble of u will evaluate on L to just a simple formal power series in the variable u inverse. So I call that chi L of u. So that encodes some central character information about that irreducible L. So was that clear? This is a very important point. These dotted bubbles in this Heisenberg, they give a kind of a conceptual way to write down central characters of irreducible objects in this modular category. K is our ground field. Kappa, where are you looking? Kappa is the central charge. That's one of the parameters that's fixed at the beginning. Okay. So how do you compute the central character, this chi L of u? Well, that's the first really cool theorem. In fact, chi L of u is not just a formal series, it's actually a rational function in u. And you can compute it by taking the polynomial NL of u divided by the polynomial ML of u. And what are M and N? ML of x is just the so L is an irreducible. You can apply the functor E to L. And this dot, this upward dot, is an endomorphism of that module EL. ML of x just denotes the minimal polynomial of that endomorphism. And NL of x is the same as the minimal polynomial of the downward dot which is an endomorphism of the functor f applied to L. Okay, so this central character, chi L of u, the central character of L, you can compute it as the ratio of these two minimal polynomials, the minimal polynomial of the down dot divided by the minimal polynomial of the up. These are all just extremely elementary results. They're proved just using relations in this Isomeric Heisenberg. But this kind of simple chain of ideas of managing central characters and relating them to these minimal polynomials, it's in all of these categorification stories, all four of them. I'm telling you the isomeric one. This is the first step. It's the same in all of them. So okay, so I have these central characters. I can calculate them if I can work out these minimal polynomials. The other thing you want to do is you want to take an irreducible object L and apply one of your functors. Maybe apply the functor E. That's how the upstrand in Heisenberg acts. So take L, apply the functor E to it to look at EL. That won't be an irreducible module, but you want to take some irreducible constituent of that, and you'd like to understand its central character if you know the central character of L. So to do that, what you have to understand is how these dotted bubbles commute past the upward string. You see, if you're imagining acting on an irreducible L, you'll know how that bubble of U acts. That'll act by this central character power series. When you act on L with this, you'll get some new module. And if you want to understand how bubble of U acts on that or on its subquotients, you need to commute this bubble past the upstream. And this is the very beautiful formula for how it happens. So I've got to explain this a little bit. So this is the upstring tensored on the left with bubble of U. This is the upstring tensored on the right with bubble U. So I'm sort of sliding this bubble through the strand. And when you do this, you get some dots produced on the upstrand. And those are dots produced on the upstrand. And I've labeled them in a rather complicated way by that you should expand that as a formal series in U inverse. The coefficients will be some polynomials in X. And I use this very handy shorthand that when I have a dot and I pin a polynomial f of x to it right here, well, if I pin x to the n to a dot, that just means the dot to the power n. And then a polynomial is a linear combination of monomials, x to the n. Once you know what I mean when I pin a monomial to a dot, you know what I mean when I pin a polynomial to a dot. And what I'm doing here is U is a formal variable. This is a generating function's worth of polynomials pinned to dots. So it's kind of one beautiful formula that's encoding tremendously complicated calculation. But this is what you need to understand what happens to central characters when you apply the functor E to an irreducible module L. Using this bubble slide, you can work out its central character. So this rational function that appears in this bubble slide, you calculate it using the relations, plays an absolutely key role. I call it P of U, X. So there's an absolutely key change of variable that you have to realize. If you take this rational function P of U, X, if you make the change of variable x squared is y plus 1, then that rational function becomes this. It still looks horrible, right? But I've managed to factorize some stuff. Amazingly, this is the key to literally everything. So understanding this trick. Okay, so I now need to go a little bit quickly. I need to introduce some affine Lie algebras. So to do this, K was our field. Let this be the equivalence relation on the field. I twiddles j if I is an integer n plus or minus j. And I need to make a choice of equivalence class representatives for this equivalence relation. I call it A. And then I'm going to introduce this set capital I, which is going to index simple roots of a root system in a minute. I is the disjoint union of these things IK. This is a little bit hard to get to cope with this. And then IK, there's various cases for what I mean with IK. If K is not equivalent to 0 or -1/2, and you're in characteristic 0, ik is just k minus 2, k minus 1, k. So it's just like a copy of, it's a coset of z where you shift to k. If k is equivalent to 0, then ik just denotes 0, 1, 2, just non-negative integers. And if k is equivalent to -1/2, it denotes -1/2, -3/2, -5/2 down forever. So this is the half place. If you're in positive characteristic, it's a little different. If you're not equivalent to 0, which is equivalent to -1/2 in characteristic P, then the set ik is just the coset of k, but now we're in characteristic P, so P is 0, so it's just a finite set. And in the exceptional case, when k is equivalent to 0, it's this set 0, 1, all the way up and stopping at -1/2. So in characteristic 0, you kind of get two cases here, but in positive characteristic, they merge into just one case. So that's just purely combinatorial definition of some sets, these IKs, and then I is their union. So I'm not going to explain those. So this is totally silly definition. To each of these IKs, there's a Dynkin diagram attached. So in the first case, this is the A infinity Dynkin diagram. In the second case, it's the B infinity Dynkin diagram. In the third case, it's the C infinity Dynkin diagram. And then in positive characteristic, you get this cyclic diagram, AP minus 1 upper 1, or in the exceptional case, you get AP minus 1 upper 2. I'm trying to explain how this root system arises out of this rational function. If you look at this rational function in the right way, you see this root system. So I'll let G be the affine algebra. So I is these IKs are these different connected components of an infinite Dynkin diagram, and G will just be the corresponding Moody algebra. And I'll use usual theoretic data. X is the root lattice, alpha I and pi I are the simple roots and the fundamental weights. And I don't want to dwell on that. And then the other complicated thing to get this business going is I also need the set J, which is you just translate, it's I plus 1/2. And there's this little function B, which is a bijection from my set I to my set J, which maps little I to the square root of I plus 1. And there's a unique choice of square root that lies in this set J. I'm sorry, that's very complicated to swallow that. But my formula from before is this change of variable to the rational function that appeared in bubble slide. You can, if you think about that, you see in this formula, the change of variable was x squared is y plus 1. And in this crazy formula for B, that's that I plus 1 is appearing. So that same formula that I wrote down tells you that if you evaluate x, the dot, at the scalar B of I, then you get this identity for this rational function P of U, B of I. And on the right-hand side, you get, well, on the denominator, there's B of I. In the numerator, you have B of I minus 1 and B of I plus 1. And this is exactly the adjacency in these Dynkin diagrams that I drew on the previous slide. Somehow, this just thinking about this rational function, you see this root system. And a few kind of weird things happen. It can be that B of I minus 1 squared equals B of I plus 1 squared. Or it can be that B of I squared is equal to B of I plus 1 squared. Just in exceptional situations. And that's where these Dynkin diagrams in these exceptional cases come from, when there's some coincidence, so there's some cancelling going on in that rational function. Okay, let me try and cut to the chase. So now, having set up all this setup, almost on the surface from the definition at this point, we've really gone very, very little distance. I had this functor E from A to A. I'm going to use E sub I to denote a summand of that functor E that you get by not taking the I eigenspace, but by taking the B of I eigenspace of the dot. Remember, the dot, it's an endomorphism of E, so you can take its generalized eigenspaces. And EI is the generalized B of I eigenspace. Similarly, FI is the generalized B of I eigenspace of the downward. So this decomposes that function E as a direct sum, E0, and then you get two copies of these other EIs. F decomposes as F0 and two copies of these other FIs. It's absolutely crucial that the change of the function B is built into this labeling, this weird change of variable that made this rational function somehow factorize in an understandable way. I also want to let epsilon I of L be the multiplicity of the number B of I as a root of the minimal polynomial, ML of X. Phi I is the multiplicity of Bi as a root of NL of X. And then remember I had that central character chi L of U, that rational function. Because chi L was the ratio of these minimal polynomials, N of U over M of U, the data of that rational function is totally recorded by the data of these numbers, epsilon I and phi I. They're the multiplicities of the zeros and the poles in that rational function phi, which is N over U. So I've just stuck them all together into this weight of L. So the coefficient of the ith fundamental weight, that's just phi I minus epsilon I. It's just recording multiplicities of zeros and poles in this rational function. So all this is just combinatorial data that you want to work out for A, kind of falls out from the setup. So then I let A lambda be the Serre subcategory of A generated by all the irreducibles of weight lambda. Remember, this weight encodes this central character. So this is just a decomposition of the category A into different kind of blocks corresponding to different central characters. And if you look at the formulas on the previous page, you can almost prove for yourself that this function EI maps A lambda to A lambda plus alpha I, and FI maps A lambda to A lambda minus alpha I. So it's kind of immediately, you need to work out what this crystal data is, depending on your A, but you get this structure theory for free in front of you. So I just wrote it down very quickly in my baby example. I'm not going to go through this calculation at all, but remember my baby example, there were three irreducibles. It's very trivial. You can work out the minimal polynomials, so you can calculate the weights. And this picture is encoding this combinatorial structure of this. You might recognize this as the perfect crystal for the Lie algebra A2 upper 2. So I'm going to hastily move along. Did they do that already? That's great. Okay, well.
Just speak loudly because your microphone.
So I'm going to just try and wrap things up very, very fast. But so far, this is kind of the initial trivial work that gives you this beautiful, nice, clean framework for encoding all the combinatorial structure of this category A. And it's kind of uniform and it works beautifully. But in fact, it's just a shadow of a much, much more wonderful story, which is passing from this isomeric Heisenberg action to an action of something called, which I just call U of G, which is the super Kac-Moody 2 category. So I think many of you are familiar with Kac-Moody 2 categories. This is the super analog, and I wrote down the definition, but it's not super important. So these Kac-Moody diagrams, they're string diagrams, but now the strings get colored by elements of the set I. And the relations here for all strings of color not 0 are the usual relations for the usual purely even Kac-Moody 2 category. For the string colored 0, the relations are the relations of the odd nil Hecke algebra. This is the super part of the story. It's only the simple root 0 that becomes difficult in this story. And so this is actually, we're nearly actually at the end here. So this is this 2 supercategory U of G for this Kac-Moody G that I just introduced. Away from I equals 0, U of G is just the usual Kac-Moody 2 category of Khovanov, Lauda, and Ruquier. But when I is 0, when you have strings of color 0, it's related to this work of Ellis, Lauda, and Khovanov, this odd nil Hecke. So the main theorem that we prove with Alistair Savage, you need one more piece of data. You need to pick a parity function from the weight lattice X to Z2, so that the parity doesn't change when you add alpha I, except when you add alpha 0. That's the weird odd root that appears here. That has to flip the parity. And then our main theorem says that from the category A, which had this isomeric Heisenberg action, we can construct an action of this Moody 2 category U of G, not quite on A. You have to, it depends on lambda. Remember, lambda was indexing these blocks, these A lambdas of A. If the parity function is 0, then you take A lambda. But if the parity function is 1, you have to take A lambda Clifford twisted. It's really quite a subtle thing. So briefly, the Heisenberg action induces an action of this Moody 2 category. And so this has suddenly, from this rather naive setup, we've reached a rather remarkable place where we have this Moody 2 category, which has an incredibly powerful structure theory attached to it that you see acting not quite on A, but on A where there's been some Clifford twists introduced. So I'm just going to finish by highlighting this last point. So one of the consequences of this, for literally any A that you started with at the beginning, is you get sort of for free out of this, you get derived equivalences between the blocks of the category A. So for each I, if I is not 0, 0 is the hard one, the odd root. For all other I's, you take the block lambda and the block labeled by SI of lambda. And this famous work of Chuang and Ruquier gives derived equivalences between these blocks. But when I is 0, it's more complicated. And you can't apply the Chuang-Ruquier theory because that doesn't know about that's the odd root where this odd-nil Hecke algebra appears. But we can show here there's an odd analog of the Ricard complex in the Chuang-Ruquier work, and together with this theory, it tells you that the bounded derived categories of the blocks, they're either when you apply S0, the odd simple reflection to lambda, they're either derived equivalent or they're derived equivalent up to a Clifford twist, depending on the parity of H0 of lambda. And so if you apply these derived equivalences to my other example, the Sn hat, the double covers of Sn example, you get, as a consequence, you get derived equivalences between blocks of projective representations of symmetric groups and characteristic P. And this is exactly enough to finish the proof of Brouet's abelian defect conjecture for Sn hat, which we were able to do with Sasha Klestchev. And an independent way of getting these derived equivalences was worked out by Ebert, Lauda, and Vera. And I've got to mention that the huge part of the work was a separate endeavor of Klestchev and Livesey, which reduced it down to getting these derived equivalences. I'm sorry that it was rather fast.
So am I right in saying like the only grading here is like the one coming from the superness, right?
I've stressed that there's no obvious grading on my A that I started with. Typically, these examples coming from representation theory don't have that obvious grading. And this Isomeric Heisenberg has no Z grading on it. But this passage that is truly miraculous to this U of G, this Moody 2 category side, that does have a remarkable Z grading in it. And so this is sort of one of the ways that it's kind of similar in I don't know, the jungle bimodule story. You apply this in that world, and you see all these sort of hidden causal gradings on your representation categories. This is how this appears in this sort of parallel world.
So is that what allows the bubbles to act like non-trivial things? Because something with the no power.
Yeah, I mean, in the Isomeric Heisenberg, you shouldn't think of that as being a great thing in any way. And these bubbles, these central characters, they're interesting. They're not, things are not just local.
And also, sorry, I'm about questions. I guess are you going to apply like the triangular base theory or the weakly triangular category theory to this this Isomeric Heisenberg setup as well?
No, I feel like that's something you should do on the Moody side.
Okay. Is that something you guys are doing?
I mean, you like,
I
okay.
think actually, when I relate them, maybe more just about some classes, so maybe you can take on the guy.